Find a power series solution for the following differential equations. Part A, the first derivative of y plus 2x times y equals 0. For a power series solution, we're going to begin with a function form and then solve for some parts of that. So y of x is equal to the sum from n equals 0 to infinity of a sub n times x to the n. And this means that y prime of x is equal to the series from n equals 1 to infinity of n times a sub n times x to the n minus 1, using the power rule, the general power rule. Now we're going to substitute these two functions, y of x and y prime of x, into our differential equation. This means that we have the sum from n equals 1 to infinity of n times a sub n times x to the n minus 1 plus 2x times the sum from n equals 0 to infinity of a sub n times x to the n, and that is equal to 0. First, we'll multiply the coefficient on our second sum into the summand. So this will be the sum from n equals 1 to infinity of n times a sub n times x to the n minus 1 end exponent plus the sum from n equals 0 to infinity of 2a sub n times x to the n plus 1 end exponent, and that will equal 0. Now we want both of these power series that we have to have the same powers of x. So I'm going to adjust my index of the second, to be equal to the sum from n equals 1 to infinity of 2 times a sub n minus 1 end subscript times x to the n. And we'll leave the first power series the same. Actually, no, we need to adjust that 1 as well. I'm going to change that to the sum from n equals 0 to infinity of, open parentheses, n plus 1, close parentheses, times a sub n plus 1 end subscript x to the n. And for the whole thing, plus the sum from n equals 1 to infinity of 2 times a sub n minus 1 end subscript times x to the n equals 0. Now, because these two series do not begin at the same place, I'm going to remove the 0th term so that we can combine them. So this would be equal to, well, a sub 1 plus the sum from n equals 1 to infinity of, open bracket, open parentheses, n plus 1, close parentheses, a subscript of n plus 1 end subscript plus 2a subscript of n minus 1 end subscript close bracket x to the n equals 0. Now we can equate coefficients, come up with a relationship for these. So because this is identically equal to 0, a sub 1 must be equal to 0. Just add that here. A sub 1 is equal to 0. But that also means that n plus 1, or parentheses, n plus 1, close parentheses, multiplied by a sub n plus 1 n subscript, plus 2 a sub n minus 1 n subscript, is equal to 0 as long as n is greater than or equal to 1, based on our index. Now that's actually a recursive relationship. So we can start evaluating for specific values of n to find out what some of our coefficients are. So So but we need to hold on to that a sub 1 is equal to 0. Now let me just rearrange this recursive relationship to say that a sub n plus 1, n subscript, is equal to 2, or negative 2, times a n minus 1, n to subscript, over the quantity n plus 1. So if I take n equal to 1, for instance, n equal to 1 would tell me that a sub 2 is equal to negative 2 a sub 0 all over 2, which would be equal to negative a 0. Okay, so a sub 2 is equal to negative a sub 0. Okay, that's fine. A sub 3 is then equal to negative 2 times a sub 1 over, well, it doesn't really matter because it's going to be equal to 0 because a sub 1 is equal to 0. So a sub 3 is equal to 0. And then if you notice, because these terms are tied with a relationship of 2, so n minus 1 as opposed to n plus 1, it actually turns out that all the odd terms will be equal to 0 because a5 will be related to a3, which is equal to 0. a7 will be related to a5, which is related to a3, which will be equal to 0. So we find this tracing back all the way. So this is actually true for all the odd terms. So let's concentrate just a little bit on a sub 4. Let me just actually write these down here. So a sub 1 is equal to 0. A sub 2 is equal to negative 2, negative a sub 0. A sub 0 was actually unknown. That's actually going to be our constant in this whole matter, this differential equation. A sub 4 will be equal to negative 2 times a sub 2, which is negative a sub 0, and that's all over 4, so that is equal to a sub 0, or 1/2 a sub 0. Well, a sub 6 will be related to that, so a sub 6 will be equal to negative 2 times a sub 4, which is actually equal to 1/2 a sub 0, and that will be over 6. So simplifying that, we see that a sub 6 is equal to negative 1 over, and I'm going to write that as 3 times 2, end fraction times a sub 0. All right, a sub 8. And at this point, we may notice a pattern and actually write out the function. A sub 8 is equal to negative 2 multiplied by negative 1 over 3 times 2, end fraction a sub 0, and all of that is over 8, which becomes all right, so that becomes 1 over 4 times 3 times 2, end fraction times a sub 0. So as I said, we may notice a pattern at this point. And I'm going to go ahead and write out that y of x is equal to a sub 0, because that's unknown, minus a sub 0 times x squared, plus 1 over 2, 1/2, times a sub 0 x to the 4th, minus 1 over 3 times 2, end fraction, a sub 0 x to the 6th, plus 1 over 4 times 3 times 2, end fraction, a sub 0 x to the 8th, and it continues in that pattern. Now, since every term has an a sub 0, this is going to be equal to a sub 0 multiplied by the sum from n equals 0 to infinity of the fraction, parentheses, -1, close parentheses, to the n, denominator of n factorial, end fraction, x to the 2n end exponent. Now, pause this and take a moment and convince yourself that that actually does hold with the pattern we've already observed. And now that you've done that, this is actually a known power series. We know what e to the x is. Well, here this is actually e to the x with an inserted negative x squared. So this will be equal to a sub 0 times e to the exponent of negative x squared end exponent. So that, finally, our solution, our power series solution, is y of x equals a sub 0 times e to the exponent of negative x squared end exponent. Or if you would rather, the power series that we had just a moment ago.